Every Android developer knows one rule: do not block the main thread. But do you actually know what the main thread is? Not what it does, what it is. Because the main thread is not magic. It is not some special construct that Android invented from scratch. It is just a regular thread running a very specific pattern, a pattern called a message loop. And once you truly understand that pattern, so many things about Android suddenly make sense. Why does calling thread.sweep on the main thread freeze your UI? Why does view.post work? Why does with context dispatchers.main resume your coroutine on the right thread? It is all the same mechanism. One loop, pulling messages from a queue, processing them one at a time. Let us open it up and see exactly how it works. Here's the fundamental insight. When your app's process starts, the main thread begins executing a method called looper.loop, and that method is essentially an infinite while loop. It looks roughly like this: loop forever, get the next message from the queue, dispatch that message from the queue, dispatch that message to its target handler, repeat. That is it. That is your main thread. It is sitting in a loop, waiting for messages and processing them one by one. Every single thing that happens on the main thread, every touch event, every view draw, every lifecycle callback, every coroutine resumption, is a message in this queue. When the system wants to tell your activity that it should call on create, it posts a message. When a view needs to be redrawn, it posts a message. When you call run on a thread, you're posting a message. The main thread is not doing many things simultaneously. It is doing one thing at a time, in order, from a queue. The message queue is exactly what it sounds like, a queue of message objects waiting to be processed. But it is a bit more sophisticated than a simple list. Messages in the queue are sorted by their scheduled time. Most messages are scheduled for now, process me as soon as possible. But you can also schedule messages for the future. That is what Anla post-delayed does. The queue is also smart about blocking. When there are no messages to process, the main thread does not busy wait or spin in a tight loop burning CPU. It calls a native method that puts the thread to sleep at the Linux kernel level using a mechanism called EPOL. The thread is genuinely sleeping using 0 CPU until a new message arrives or a scheduled message's time comes. Then it wakes up, processes the message, and either processes the next one or goes back to sleep. This is incredibly efficient. So how do messages get into the queue? That is the handler's job. A handler is an object that is bound to a specific looper and its message queue. When you call handler.post with a runnable, the handler wraps that runnable in a message object and inserts it into the message queue. When the looper eventually pulls that message out of the queue, it calls the runnable's run method on the looper's thread. This is the entire mechanism behind thread communication in Android. Want to run something on the main thread from a background thread? Get a handler that is bound to the main looper and post to it. That is exactly what run on with thread does under the hood. It checks, am I already on the main thread? If yes, just run the code directly. If no, post it to the main thread's enna. View.post does the same thing. It posts a runnable to the view's enna, which is the main thread's enna, which is the main thread's enna. Even with context dispatchers, main in coroutines ultimately uses a enna there to post the continuation back to the main thread's message queue. I want to really drive this point home because it is foundational. When the user touches the screen, the input system creates a message containing the touch event and posts it to your app's main thread queue. When the system decides it is time to draw a new frame, it posts a message. When your activity needs to move from one lifecycle state to another, it is a message. When a coroutine completes on dispatchers.io and needs to resume on dispatchers main, the continuation is wrapped in a message and posted to the queue. When you call setText on a text view, that eventually triggers an invalidate, which schedules a message for redraw. Every single UI operation is a message. The main thread processes them one at a time in order. There is no parallelism on the main thread. There is no preemption. If a message takes 200 milliseconds to process, every other message, including the one that draws the next frame, waits 200 milliseconds. This is why blocking the main thread is catastrophic. Now you can see why blocking the main thread causes junk or a total freeze. Imagine the queue has 20 messages in it. Touch events, draw commands, lifecycle callbacks. The looper pulls the first message and starts processing it. But that message involves reading a file from disk, which takes 500 milliseconds. For that entire 500 milliseconds, the looper cannot process any other messages. Touch events pile up in the queue unprocessed, so the UI feels unresponsive. Draw messages pile up, so the screen looks frozen. The choreographer posts a message saying it is time to draw frame number 1000, but the looper is stuck processing your disk read. By the time it finishes and gets to the draw message, it is too late. You have missed multiple frame deadlines. The user sees a frozen screen. This is what makes the main thread so precious. It is a single lane highway. If one car stops, everything behind it stops too. There is no way around. Speaking of frames, let us talk about the choreographer. The choreographer is the system's frame clock. It coordinates when animation, input, and drawing happen. On a 60 Hz display, the choreographer triggers a callback roughly every 16.6 milliseconds. On a 120 Hz display, it is every 8.3 milliseconds. When the choreographer fires, it posts a special message called the frame callback. This message tells the system to process input events, run animations, and then do the measure, layout, and draw passes. All of that has to happen within one frame period, 16.6 milliseconds for a 60 Hz display. If your app takes 20 milliseconds to process a frame, you have missed the deadline. The display will show the previous frame again, and the user perceives jank, a stutter or hitch in the animation. This is why performance-sensitive code on the main thread needs to be fast. Not just fast enough to avoid ANRs, fast enough to finish within a single frame. Let me show you some common patterns so you can recognize them in code. Handler.post takes a runnable and schedules it for immediate execution on the handler's thread. Handler.postDelayed takes a runnable and the delay in milliseconds. This is how you schedule future work on the main thread, simple animations, timeouts, debouncing. Handler.post at front of queue inserts a message at the front of the queue instead of the back, which means it runs before any currently queued messages. Be careful with this one, it can break expected ordering. You will also see handler.sendMessage, which sends a raw message object, but fodder.sendMessage, which sends a raw message object. This is more common in framework code than in app code, but it is useful when you want to use the messages what field to distinguish between different types of messages in a single handler. All of these are just different ways to put messages into the same queue that the looper processes. Here is something a lot of Android developers do not know. You can create your own looper on a background thread. That is what handler thread is. It is a thread that sets up its own looper and message queue, and then sits in the same infinite loop, processing messages one at a time. Why would you want this? Because sometimes you need a background thread that processes tasks sequentially, in order, without concurrency. Think about writing to a log file, or sending analytics events, or managing a serial connection. You do not want multiple threads writing to the same file simultaneously. A handler thread gives you a single-threaded ordered execution queue, just like the main thread, but on a background thread. Intent service used to be built on handler thread, and many Android system services still use this pattern internally. There is one more piece of the message queue that is really elegant. Idle handler. You can register an idle handler callback on the message queue and it will be called whenever the queue becomes empty and the looper has nothing to do. This is perfect for deferring non-urgent work until the main thread is idle. Need to initialize an analytics SDK? Do not do it in application on create. Register an idle handler that initializes it once the first frame has been drawn and the queue is empty. Jetpack's app startup library uses a similar concept. Glide and other image loading libraries use idle handler to clean up resources. The callback returns a boolean, return true if you want to keep being notified of idle periods, or false if this was a one-time thing. It is a small API, but it is incredibly useful for optimizing startup time and keeping the main thread responsive. Let us connect this to coroutines, since that is how most modern Android code manages threading. When you write with context dispatchers.main, what actually happens? Dispatchers.main is backed by a handler that is bound to the main thread's looper. When a coroutine needs to resume on the main dispatcher, the dispatcher posts the continuation, which is just a runnable, to the main thread's message queue via that handler. The coroutine machinery does not do anything special. It uses the exact same mechanism as run on UI thread or view.post. It is all messages in the queue. This also means that if you call with context dispatchers main and then do something that blocks, like calling a synchronized method that is held by another thread, you are blocking the main thread. The coroutine does not save you. Dispatchers main runs on the main thread, and the main thread is still that single main highway. Suspending is fine, blocking is not. Let us recap. The main thread is a message loop. Looper dupe pulls messages from a message key and processes them one at a time. Handlers post messages into the queue. Every UI operation, every touch event, every lifecycle callback, every coroutine resumption on dispatchers ends. All messages in the same queue. Blocking any single message blocks everything behind it. The choreographer posts frame callbacks every 16 milliseconds, and if your code does not finish in time, you get jank. And the thread gives you the same pattern on a background thread. Idle handler lets you defer work until the queue is empty. In the next video, we are going to follow what happens after the choreographer fires, the rendering pipeline. How does a view go from a Kotlin object in memory to actual pixels on a screen? That is measure, layout, and draw. See you there.